Welcome to Semantic Web Technologies. This is lecture number 6, Applications in the Web of Data. And today I want to talk to you about named entity recognition. So what is this? As you remember, our language is able to represent objects of the real world with the help of symbols. So for example, Jaguar stands for an object which resembles what you see here, either a cat, a car, or the operating system Jaguar. Usually, a lot of other factors are required to solve this ambiguity issue. So for example, you need the context. Also, you need to know what is the pragmatics of the one who communicates the message that consists out of the symbol. And also it depends on your own experience, how you interpret it. So we know that sender and receiver must use the same concept to understand each other. But for us, especially the process that is between the symbol and the concept is rather important, because for the machine, up to now we do not know how to map, for example, a symbol here to a concept, which means an ontology or an ontology representation. And this will be subject of today's lecture. Okay. So just imagine you will get this message or this symbol, Armstrong. What does it mean? The problem is it's ambiguous, so it has several meanings. It could refer to a person, Neil Armstrong, Louis Armstrong, Lance Armstrong. It also could refer to a location, Armstrong County, for example, or the Armstrong Tunnel, or something else. So what we need more information. We need context information to get it right. So if I give you this context, then it might be pretty clear that Armstrong refers to Neil Armstrong. So the problem is Armstrong here is more than just a character string. Neil Armstrong, we have to know this, is an astronaut. And of course, an astronaut is some kind of a science occupation. And a science occupation is some kind of an employment. On the other hand, we know that Neil Armstrong refers to a person. And we also know that a person has an employment, or can have an employment. So you see here, this is the knowledge. We have already talked about knowledge, and here the entities, and here the ontologies. And we even know more. We know, for example, that a person is not the same as a science occupation. And on the other hand, we can also say that an astronaut is the same as a cosmonaut, which is the Russian or Eastern expression for an astronaut. And for example, we have one very famous astronaut from Russia, Yuri Gagarin, and then we can, because we know the classes here are related somehow, we can also deduce relations among the entities that the classes refer to. So this is the knowledge. And to get from a string or a symbol to the knowledge representation, or to get the mapping between this process is often called named entity recognition, or also entity identification or entity extraction. And this denotes the location or locating and classifying atomic elements into predefined categories, such, for example, names, persons, organizations, location, expressions of time, quantities, monetary values, etc. Or even on a more fine granular level, you can map the entity directly to a semantic entity which is connected to an ontology. So not only to a category or to a classification, but to a named entity. So this is named entity recognition. Okay, where does the knowledge come from? Of course, we know that, for example, Neil Armstrong is represented in the Wikipedia, and also we know that in the Wikipedia we have these info boxes, and from these info boxes we finally get to the DBpedia. So we have the entire web of data, of linked open data, to map this string Armstrong to. So what we have to find is a mapping between the string Armstrong and, of course, the referring article in the DBpedia to Neil Armstrong. And the problem is here in the entity mapping process to find the right one. So if we come back to our semiotic triangle, we see that here the process from the symbol coming to the concept. So this mapping process is here the most important one. And you see here Armstrong, of course, might refer to the astronaut, the man on the bicycle, or here to a city in British Columbia, which is called Armstrong 2. So To decide this, we already said we need context. Okay, let's look at an example. For example, context can be given also in terms of characters or other symbols. So for example, we have here a text or a sentence in natural language. Armstrong landed the eagle on the moon. So we have lots of ambiguous terms in there, at least ambiguous nouns. And what we have to do, or when we try to disambiguate these concepts and try to map the right ontology, the right entity to these strings, of course, we have to take into account all possible meanings. So the first thing that we try to do is, okay, we try to identify all ambiguous terms, here the nouns, and we try to determine all possible entity mapping candidates. So first of all, there we have to do a linguistic analysis of this text. This is called part of speech tagging, where each component, the nouns, the verbs, the adjectives, are categorized and the nouns are classified. Then there must be some normalization process. We have to look at different encodings and spellings, because in Armstrong, this is a pretty simple example, but if you have symbols or names that come from other languages, then you have to transcode these characters, these special characters. They are language dependent, and there are language dependent different spellings of names, for example. It's also different abbreviations, different acronyms, and of course type dependent spelling. So do you put the first name in front of the surname, or do you write first the surname, then a comma, and then the first name? So you have to take this into account, of course. And there might be alternative names and synonyms. And also you have to consider fuzzy string mappings. So in the end, when you look for Armstrong in the DBpedia and you consider all possible mappings, you will end up with quite a lot, or a huge set of simple entities. So there are more than 400 entities that refer to Armstrong. You see here, for example, we have Armstrong, Ontario, which is a location. We have Armstrong, which is a car manufacturer. We have Armstrong County in Texas. We have Louis Armstrong. We have the Armstrong Tunnel. We have Greg Armstrong. We have Gary Armstrong, whoever this was. And we have also, in the end, Neil Armstrong. But we must determine the right one. So this is difficult. It's a difficult process, not for us, because we have our experience and we know how to read and interpret this context, but for the machine, of course, it's difficult. So we have to determine all possible mapping candidates, and finally we have to choose or develop methods to determine the right one, to determine that Neil Armstrong is really the right entity we are looking for. And for this we have to determine context and, of course, ambiguity of the source data, ambiguity of the mapping. They all determine the accuracy and the reliability of our mapping and of our data. So this has to be taken into account. And you do this not only for the Armstrong, you do this also for the other nouns here in the sentence, for the eagle and for the moon. And in the end, you will see you end up here with 448 entities for Armstrong, almost 100 entities for the eagle, and more than 100 entities for the moon. So, and now you have to check each possible combination, which one is the one that is most likely the right one to match here. So you see, now this task is getting a complex task for the machine, because lots of comparisons and lots of computations have to be performed here. So how does the mapping strategy, the named entity recognition strategy work? There are several strategies to do that. So you have to take into account, for example, the popularity of the symbols and the entities. Maybe Lance Armstrong is rather popular today because he was in the news, more popular than Armstrong County, for example, because it was not in the news. So this would be some kind of a popularity-based strategy or heuristic to choose a well-suited entity. Then there are linguistic and statistical strategies. So for example, if you refer to a large corpus of documents, for example, if you look at the texts that are represented in the Wikipedia, then you can look up all these possible candidates or candidate terms within the Wikipedia pages of your entities, and you can see whether they do co-occur, so whether they occur both or all in one single page. So this would be quite nice, because then they were put into the same context, and then it's much more likely that they really belong together. And then there are also semantic strategies that work quite similar, but they do not use the Wikipedia. But on this hand, they use the DBpedia, of course. So the means that you use here are reference text corpora like the Wikipedia. You use the link graph from the Wikipedia and the semantic graph from the DBpedia. And in general, with each of your strategies, you can work in the following way. You follow a general approach. First, you make an assumption about which would be the right entity to choose. And then you ask, do these strategies really support or contradict your assumption? And finally, you make your decision according to logical and probabilistic rules and constraints that you have put there in advance. So this is the general strategy. I will show you one of the strategies. Okay, for example, try to map Armstrong to some Wikipedia pages. For example, I can try to map Armstrong here to Louis Armstrong. I can try to map the eagle to the eagle, means the bird, the animal, and I can try to map the moon to Fly Me to the Moon. At least we know that Louis Armstrong and this song here, Fly Me to the Moon, have something in common. But you will see it's much more likely that here the Wikipedia page of Neil Armstrong has something to do with the Wikipedia page of the Apollo Lunar Lander module, which was called Eagle. And this, of course, has something to do with the moon, the planet moon. So what you can do here is, for example, you look at the texts and you try to find Eagle, Moon, and Armstrong in all of these pages. And then you can also take into account the number, how often they do occur together, for example. And this is called a co-occurrence measure. And this is a statistical and linguistical measure that can be used to decide which is the right context, which one is the right entity, which should I choose for disambiguation. And the same can also be done via the DBpedia link graph. You just look at the links that are between the entities, and then maybe between these entities you might find links. And the thing we are looking for are so-called connected components. So here, for example, we have a connected component between Neil Armstrong, Eagle, which is the lunar lander module, and the moon. There might be other connections, but in a closed connected component, there, for example, it's much more likely that these three entities together form a context with a high probability, and they can be matched against these symbols that occur in the same context. So what we would do here is we would then map the strings or the nouns to the according URIs that stand for the entities we have determined in the mapping process. So this is the process called named entity mapping. Whenever you have named entities that can be mapped against natural language expressions in some text corpora, you can use, of course, these URIs as a semantic annotation, because this URI denotes an entity which refers to an ontology where the knowledge about this ontology is stored or represented. So this is semantic annotation. And this semantic annotation can, for example, also be used in the search process, in the information retrieval process, to improve the information retrieval process. And this is something we want to look in the next part of the lecture when we are dealing with semantic search.